ladies and gentlemen, my name is Václavík. I am from Research Institute from Pilsen, Czech Republic, and I would like to tell you something about fatigue behavior of hybrid beam, which is a common work of our firms in Czech Republic and also from Solaris from Poland. So I would like also say many greetings to my colleagues from Poland, which have not the possibility to go here and are online. So here is the content of my presentation, and the motivation is that new high mass equipment of buses increase the mass of buses, decrease the space and limit the available passenger capacity of the bus. And solution for this can be to use hybrid materials, so some composite profiles and nodes, sandwich structures, and so on. Our idea in this project was to use very easy solutions. So use the CFRP plates which are glued on the structure on the hollow beams, and also to fill these hollow beams with some foams. But the basic considerations are to solve this is that this CFRP plates has not be debonded during the operation of the bus, because still for long time operation of the bus, still the bus may have some accident, as for example rollover accident, and the structure must withstand this high plastic deformation, and the CFRP plates has not be debonded. We use this ferritic stainless steel, which is used also for bus structure design. Pearl-threaded CFRP plates, Sika Carbodur S512, and structure adhesives, Sika Power 1277. We have also calculated this using stress-based approach, this maximum allowable shear stress and pinning stress on the end of the CFRP plate, and for 20 megapascal allowable shear strength in the adhesive, the normal stress on the spacements or on the profiles can be only 230 megapascals, which is lower value than the yield limit of the material. But when we put this plates from both sides, then the allowable limit increase to approximately the yield point of the material. During fatigue test, we observed the debonding of the CFRP plate, especially with strain gauges, and according FEM support, it was calculated that when we measure 5 millimeters strains, 10 millimeter strains from the edge of the CFRP, then when the stress or strain decreased by the factor 1.71, the CFRP plate is unbonded to 5 millimeters, and this is our criterion for then evaluating this SN curve, that 5 millimeter is sufficient debonding for the structure. Here is example of fatigue test of flat spacements. We have this CFRP plate 140 millimeter length, and we also measure the distribution of strains from the end of the CVRP, and according to this, we can make calculation. We can calculate this distribution of shear stress in the adhesive, and also the distribution of the stress of the CVRP plate. So you can see that after about 35 millimeters, the stress is stabilized. Here are evaluated SN curve. On the left side, you can see the measurement of strain gauges and also this change of stiffness. The stiffness, the change of stiffness was not so good parameter for debonding, for small debonding evaluation. Only when the debonding was in a part of centimeters, so it was possible to observe the drop of stiffness. On the right side, you can see this SN curve for steel without CVRP plates, and also these circles, foot circles, are the points which are evaluated for 5 millimeter debonding. So this SN curve for a sample with CVRP plate is a little bit shifted to the lower service lives. Another part which we are tested was the structure part of the structure of the bottom part of the bus. We have some support of FEM calculation where to put the CVRP plates. On the left side, on the bottom, you can see the test in our laboratory, and on the right bottom there is some cracks which appears and goes under the CVRP plate, but this crack appears after a longer time than when we have the steel part without CVRP. And here is the evaluation of the fatigue test. On the left side, you can see that the bottom two lines, there is stress on the before and on the CVRP plate. So the end of the CVRP plates are not debonding, but they are forming cracks on the vertical welds, which are connected to hollow beams. And here is two SN curves. The left is without CVRP and the right is with CVRP. Here are only some examples for monitoring, also with using another techniques for monitoring. So we use ultrasound, we measure with thermocamera. We have also digital image correlations, and also we use this distributed fiber optics sensors for measurement the strains on whole lines through the sample, which it was integrated in the adhesive. This is an example of another structure part, which was side wall from the bus, and on the right side there is the monitoring the distortions during the towing tests during 2 million cycles. So conclusions: the use of stiffened hollow profiles with CVRP plates can on several joints increase the strength of the bus structure. This results in an increase in service life and a delay in the occurrence of cracks and their propagation. The beginnings and ends of the CCRP plates must lie in areas under the demanding limit stress. These areas can be determined using FEM calculation and verified using measurements with strain gauges. In properly designed hybrid structure, the hybrid beams must not delaminate during the bus service life to be able to withstand the rollover accident. So next steps is rollover simulation, application of CCRP plates to selected beams on real bus structure, and operational stress with the bus. Thank you for your attention.